Hi all, hope all of you are in good health and you are safe. So let us start the today's session with HDB3 coding. Before going to HDB3 coding, we will understand why it is required. Okay, we know that the bipolar NRZ coding technique is very useful because of its characteristics which we have studied, but there are shortcomings. What are these shortcomings? The shortcomings are when we have a long strings of zeros. As you can see in this example, yes, long strings of zeros are there. Because of this, there will be a DC level inherent in this code. There will be a DC level inherent in this code, which is not required for us, and it will affect the performance of the receiver. Apart from that, the long strings of zeros makes the receiver work tedious, because as the number of zeros increases, the clock recovery and synchronization will not happen properly. So so as to overcome these two difficulties, the synchronization and clock recovery and the DC level, okay, so as to overcome these difficulties, the bipolar NRZ has been modified to get HDB3. So this bipolar NRZ is also called as alternate mask inversion. That already you know, plus 1 is represented by plus A, the subsequent one will be minus A, then plus A, zeros will be represented by 0 voltage level. Okay. What is the difference between this AMI and bipolar NRZ? The difference is very simple. HDB3 means high density bipolar 3 encoding. Here plus 1 is represented by 1, 0 is represented by 0, the subsequent one will be represented by uh, the alternative voltage level compared to the previous voltage level. If previous is plus, then it will be minus. If previous is minus, next will be plus, likewise. Okay, that is as same as AMI. But the difference is when you have more than 3 zeros, the depending on whether the previous number of ones previous to these 4 zeros, okay, here we have one positive level, correct? If we have two ones, either plus or minus, two ones, then it is even. Now it is only one present before these 4 zeros, then it is considered as odd level. For odd level, we are going to add a violation, 3 zeros followed by violation instead of 0 level here. This violation should have same sign as the 1, which is previous bit. Okay, this is plus, that's why it is plus. If it was minus, then it should be minus. It is violating, right? Instead of writing 0, we are having a positive sign, correct? That's why it is violation. Next, you can see 1 will be opposite of this, as it is following AMI again. Now this one will be plus 0. Understood? This is a simple example. Now we'll go for next example of the same kind, HDB3 coding. This is the sequence, correct? This is AMI 0, 1, 0. The next one is minus A. These are 8 zeros are there, so it is depicted by 0 level. Then 1, next 5 zeros are there, it is 0. Now we'll see how HDB3 can be done for this. So here 0 is represented by 0, 1 is 1, again 0, 1 is minus 1, correct? Now we have 8 zeros. First we consider first 4 zeros. Before that, how many ones are there? This is 1, this is the second one, second bit, which is having some voltage level other than 0. So these are even ones before 4 zeros. So we have to represent this as B00V. B means bipolar. Bipolar means this is minus, means it should be plus. And violation is what? Violation is the rule. If this is plus, this should have been minus, right? But we are getting plus over here, correct? That's why this is a violation, and instead of writing 0, we are writing plus. We are having some voltage level, correct? That's why for E1 we represent 4 zeros as B00V. This is plus because this was minus. If this was plus, this should have been minus, and this also should have been minus. Okay, let us see next 4 zeros. Next 4 zeros are there, but we have 0 ones. We have 0 ones or 0 violations after this, correct? That is considered as E1 only. It is considered as E1. That's why we have the bipolar. Bipolar means polarity has to be changed with respect to the previous bit. Next 00V. V is violation. Violation in the sense we already know that this is minus, means this should be minus. Okay, next 1 is there, automatically it will go to the positive level, because you know that it should be alternative mask. Next 4 zeros are there. You can see here there is only 1, correct, which is odd. After the violation, how many ones are there? Only 1. That's why this is, we represent 4 zeros by 000V. If we had even number of ones, then we should have represented by B00V. Now it's only V. What is the sign of V? It should be same as the previous one. I hope you have understood this. The next one is B3ZS. B3ZS is bipolar with 3 zeros substitution coding. In this it is very simple. Instead of having 4 zeros, if you have 3 zeros, the same process is going to be repeated over here. Okay, you can see odd number of ones followed by 3 zeros, 00V. The sign is of this positive previous bit. Next is 0, 1 is opposite of this. Next 0, 1, 1, 1, correct? Now you can see 3 zeros are there, but how many zeros we have ones we have encountered before 3 zeros? 1, 2, 3, 4. 4 bits of ones after the violation. That's why it is even number of ones before these 3 zeros. So we can encode it as B0V. Here it was B00V. Here it is B0V for even number of ones, and 00V if it is odd number of ones before the 3 zeros. Yes, this is about B3ZS coding. Next one is B6ZS coding. It is very simple. If you have 6 zeros, then you are going to represent the code as 0VB, 0VB. That's it. Other things, that is 1 is represented by 1, subsequent one will be -1, 0 will be 0. And I hope you have understood all these codings. For better understanding, first read the notes and then go through the video once again. Okay, and in the next video I am going to discuss problems on pre-envelope and complex envelope. Thank you. Have a good day.